to talk about the force diagrams for loops, scoops, and hills. Imagine my marble's going around this loop. I go up, I have a force diagram, I go down, I have a force diagram, then I go over the hill, I have a force diagram, and maybe there's a scoop. The scoop and the bottom of the loop are going to be exactly the same. But this is how to do force diagrams. If you also have a side of a loop position, we'll talk about how to do that too. The easy thing to start with is that all of these have the weight on them. Every single one has the force of gravity. The force of gravity I calculated a while ago to be 0.05 newtons. I'm going to have the force of gravity from the Earth on every single one of these. Force of gravity, force of gravity, force of gravity. All right. Now we're going to talk about normal force. That's where it gets really interesting. So let's talk first about the bottom of the loop, because I think that's the easiest to kind of think about. At the bottom of the loop, there's going to be a normal force, and the normal force is going to be perpendicular to the loop. So I'm going to change my picture here so that my loop is pretty much flat to make life easier for myself. You should do that too. At the bottom of the loop, an object, the marble, in motion would like to remain in motion in a straight line, so it wants to go straight. Gravity is actually pulling it down. And if I just left it there, it would go in a curve downward because gravity is pulling it down. But something's got to be making it go up because it goes up. So it's got to have some upward acceleration. The only thing that can be pushing it up is something it's touching, and that's got to be the track. So I've got normal force from the track, and it's got to beat out gravity in order to be so powerful to move the thing upward. So my normal force in this case is going to be much bigger than gravity. How much bigger than gravity? We can actually figure that out. We did not learn this in class, but the net force in the centripetal direction, that means as you're going around a circle, the into the center of the circle pointing net force is equal to the mass times this thing, which is the centripetal acceleration. And it's the velocity squared divided by the radius of the loop. By now you've already calculated the velocity. I don't remember exactly what my numbers were, but let's say the velocity at this point was, I don't know, 2 meters per second. And let's say I measure my loop's radius at 0.2 meters. To figure out the normal force, I'm going to do some math. I'm going to say net force equals mass times centripetal acceleration. My net force is normal, because that's into the center of the circle, minus weight, that's out. You know how up is positive and down is negative, or right is positive and left is negative? Well, circle forces, in is positive and out is negative. Centripetal is positive, centrifugal is negative. That's going to equal my mass times my velocity squared, which I get from my other energy, divided by my radius, 0.2 meters. So if I do the math on this, 0.005 times 2 divided by 0.2, I get normal force minus 0.05 equals 0.1. Add 0.05 to both sides, and my normal force is going to be 1.05 newtons. That's a pretty big normal force. In fact, it's pretty huge. 1.05 newtons. So it should be a lot bigger. If the marble were really a person here, they would pretty much die. We can calculate this exactly, this centripetal acceleration, and we got v squared divided by r. This alone is 20 meters per second squared. That's twice the amount of acceleration you would normally feel from the force of gravity. Your numbers will actually probably be much higher than that. You'll be around like 7 to 12 times the amount of acceleration due to gravity, which means that if there were a real person going through your coaster, they'd be completely dead, because people can only survive up to like 7 to 9 meters per second squared. On real roller coasters, they don't have this problem because they actually make cycloid loops where the radius at the bottom is very big, and that makes this radius, this number, much bigger at the bottom of the centripetal acceleration, so you do have a smaller acceleration, and you don't black out or die on a roller coaster ride. But in order to make marbles go around coasters, we're not worrying about that, so our marbles, if they were people, are going to be dead. So those of you who have themes of like death for roller coasters, you can use that. Okay, so that's the bottom of the loop. We're going to basically do the same thing at the top of the loop. At the top of the loop, the marble wants to go straight, but it's actually going to go down. Maybe gravity is enough to pull it all the way down. Yay, maybe not. If anything, the normal force is going to go downwards. And to figure out the net force, now we've got two forces into the center. So we add the acceleration due to gravity. Sorry, we add the force of gravity, and that's going to equal the mass times the velocity at that point divided by the radius. Velocity gets squared. Now, again, I don't remember what my numbers were, but you know that the velocity at the top is going to be a lot less than the velocity at the bottom because I've lost energy going up. So let's just guess that my velocity up here is 1 meter per second. You would be finding that from your energy calculations. You would already have your velocity, so you could plug it into here. You can't get the number for the normal force unless you've already done the velocity. So I've got 0.005 times 1 divided by 0.2. My net force here is 0.025. So normal force plus 0.05 equals 0.025. I subtract 0.05 from both, and I'm going to get a mess. I'm going to get my normal force being a negative number. This will probably happen to you. What this means is you've calculated too much velocity when you were doing your energy calculations. And in order to go around like that, the normal force would actually have to be like sucking it in. What really would happen this fast, with these numbers, is that it would fall off the loop. And some of your marbles actually do that. They kind of jump from here down to there. They kind of skip. They're falling too fast and then they get caught by the loop again. That's what happens on most of these roller coasters. So if you get a negative number, that's fine. You did the math right. Give us your negative number. And the reason you've done that is because either there really is no normal force at all, it's zero because your marble is falling off the loop, or possibly there is a situation where when you did your energy calculations, you assumed too much energy, you didn't have enough friction, your velocity was too fast, and that meant that there were problems here, or your velocity was too slow. Don't worry about it. Just get the number, do the math. We want to see that you can do the math, and that you know that a negative normal force means there's a problem here. You can make some guesses as to what the problem is. Okay, so on the side of the loop, actually, you know what? I'm going to do that on a separate video.